Hi, this is Dr.G.Vikas. In this session, we'll discuss a few problems on Euler's crippling load. So, a solid round bar of 60 mm diameter and 25 meter long is used as a column. Find safe load for the following conditions when both ends are hinged, both ends are fixed. Take E is this value, a factor of safety is 3. Okay. Now, what is given? Read the question carefully first. A solid round bar of 60 mm diameter and 25 meter long. So, this is a column. What is the length of the column given? Length is 25 meter. So length of the column is 25 meter, that is 25,000 mm length L. Okay, now 60 mm diameter. So diameter, the cross section is of the this column is circular. Okay, what is the diameter given? Diameter is nothing but diameter is given as 60 mm. Okay, so D equals 60 mm. Okay, now find safe load. Okay, for these two conditions. Before finding safe load, we need to find the buckling load. Okay, so we know the formula for buckling load. So we have two conditions here. So first condition is when both ends are hinged. So we know that when both ends are hinged, this is the case. Okay, effective length will be equal to L. Okay, now what is the formula? Euler's crippling load formula. This is the formula. Pi square E I minimum by L E square. So here for first case L E is equal to L. Okay, so I minimum is nothing but for circular cross section I minimum equal to I max. So I x is equal to I by y. So the formula is 5 by 64 times diameter power 4. So substituting all this, so I minimum equal to pi by 64 times diameter power 4. Diameter is 60 power 4. Okay, this is the value. So substituting all the values, pi into E, this is E. Okay, and this is I minimum, which we have calculated already, divided by 25,000 whole square. L effective length equal to L. So this is the value. So this is your Euler's buckling load. Now safe load equal to Euler's buckling load divided by factor of safety is given as 3. So this is your safe load for first case. The second case, when both ends are fixed. When both ends are fixed, so the effective length is equal to L by 2. Okay, so here L by 2. So in the question he has not mentioned this use Euler's formula, whether he has not mentioned that thing, and he has not mentioned that it is a long column or short column. But how we come to know it is a long column and we have to apply the Euler's crippling load formula means, here we need to check, see, effective length divided by diameter should be greater than 12, then it is long column. So this ratio is LE divided by D, 2500 divided by 60. Yeah, 25,000 divided by 60, so 416.6, which is greater than 12. So it is a long column. In that way, we have decided that it is long column and we have applied crippling load, Euler's crippling load formula. Here also we need to check whether it is a long column or a short column. So LE divided by D. So here effective length when both ends are fixed, effective length equal to original length by 2. So 25,000 divided by 2 is this value. Divided by 2 is 12500. 12500. Okay, so which is divided by LE by D is 208.33, which is greater than 12. So it is a long column. Okay, therefore we have applied this formula, Euler's buckling load formula. So now substitute all the values in this formula. So E is same, this is same, and here in the place of LE we need to add this L by 2, that is 12500. Okay, then we will get this value. Okay, so safe load equal to Euler's buckling load divided by 3. This is the answer. Okay. Similarly, if you see the next problem, a steel bar of rectangular cross section. Okay, a steel bar of a rectangular cross section. The cross section is rectangular. Okay, this is section 40 by 50. Okay, this is 40, this is 50. Okay, 40, 50. Pinned at each end. Okay, at each end it is hinged at top and hinged at the bottom. Okay, and is subjected to axial compression. Okay, the bar is 2 meters long. What is the length? 2 meters. Determine buckling load and the corresponding axial stress. We need to determine this PE value we need to find, and corresponding axial stress we need to find using Euler's formula. Also calculate slenderness ratio if the proportional limit of the material is 200 Newton per mm square. So lambda we need to calculate. Okay, proportionality limit is compressive stress is 200 Newton per mm square. Take E this value. Okay. So now these dimensions are given, cross section dimensions, length is given, two ends hinged, so this will be effective length will is equal to original length. Okay, now we need to find PE. Okay, PE we need to find. Euler's buckling load we need to find, axial this compressive corresponding axial stress we need to find, and lambda we need to find. Okay, so we know that for this case L equal to L, so this is the crippling buckling load formula, Euler's buckling load formula. So all these values we know, L equal to L. But what is I minimum? Here I minimum, I maximum we need to calculate. That means IXX, IYY we need to calculate. So that whichever minimum that we need to write here. So here if we calculate this one, so here IXX equal to BD cube by 12, IYY equal to DB cube by 12. So if we can solve this, this is less, so IYY. So instead of I minimum I will replace IYY value. E is as it is, L is L. Okay, so first question is over. This is the buckling Euler's crippling load. Okay, next axial stress. Stress is load by area, so this is a load divided by area. Okay, this is the axial stress. Next, how to find the slenderness ratio lambda? Lambda equal to, we know that lambda equal to, and what is the actual formula? Effective length by radius of gyration, where radius of gyration equal to under root I by A. Okay, from here we can write k square equal to I by A and I equal to k square A. Okay, now coming to Euler's formula, this is the Euler's formula. So instead of I minimum I can write k A into k square, from this I equal to k square A. So here I have written k square into A, k minimum square into A. Okay, so here what is load compressive stress into area? So instead of here I have written compressive stress into area, instead of this same as it is here we have written here, but k square is taken down here, so Le by k, but what is Le by k? Lambda. So instead of this I have written lambda square. A gets cancelled, so if I take lambda to this side, lambda square equal to pi square E by sigma c, so lambda equal to under root pi square E by sigma c. E we know sigma c is given as 200, so this is a lambda. Thank you.